Chemistry powers today, but courageous chemistry is shaping our tomorrow. It's fueling the hydrogen economy and driving clean energy. It's in our semiconductors and even powers our 5G. It makes bridges stronger and medical equipment safer. Chemistry powers progress and binds us all together. But there's something more that sets us apart. Courageous chemistry.
Welcome to today's lesson. In today's lesson, we'll look at a very important concept known as the mole. Okay? The mole concept. Under this topic, we'll look at the meaning of mole, and then we'll also look at how to convert mole to other units. And also, we'll look at a very important theory known as the mole theory. And finally, we're going to carry out a molar mass calculation. Alright, when we talk of the mole, it is a very important concept. It is used to determine how things are measured in terms of the atomic level. For example, look at this diagram. Avogadro, who is a scientist, discovered that 1 mole of heavy substance is equivalent to 12 grams of carbon-12, and it is equal to a constant number known as Avogadro's number. This number is 6.022 times 10 to the power 23 atoms or particles, or ions or electrons. So pay attention to this video to learn more about this concept, okay?
So it makes sense that we would use a large number to help us count the number of atoms or molecules in a substance. That specific number, 6.022 times 10 to the power 23, is known as Avogadro's constant. It gives us the number of particles in a mole. Don't worry about needing to remember this. It's going to be given to you on your formula sheet. So in other words, no matter what substance you're talking about, we say a mole of it is 6.022 times 10 to the 23 particles of it. So now that we know what a mole is, it makes sense that we should be able to convert between an actual number of particles and number of moles. We know that there is Avogadro's number of particles in 1 mole, so converting from number of moles, which is written as a lowercase n, to particle number, we simply multiply by Avogadro's number, which is given by this symbol, and it's made pretty obvious by this little a here. Of course, the opposite direction applies too. Converting from number of particles to number of moles requires division by Avogadro's constant. Okay, great. So let's do a couple of examples. There's 6 moles of a substance. How many particles is this? Well, 6 multiplied by Avogadro's constant gives us 3.613 times 10 to the power 24. Alright, if I have 11 times 10 to the power 23 atoms, how many moles do I have? Well, 11 times 10 to the power 23 divided by Avogadro's constant equals 1.83 moles. Oh, easy peasy. So I can almost hear you guys saying, yeah, it makes sense that we use a really big number to count molecules and atoms, but 6.022 times 10 to the 23 seems a bit random, doesn't it? Well, you're right. It is a pretty weird number, but it's like that because it's been specifically designed by chemists to be the most useful number possible. 1 mole is defined as the exact number of carbon-12 atoms weighing 12 grams. Carbon-12 is chosen as the reference point for most things to do with comparing elements, and so this is no different. This is so useful since we can use this to relate the mass of a substance to the amount of moles. The atomic weight, or relative atomic mass on the periodic table, is in atomic mass units, AMU, and tells us the mass of 1 mole of a substance. So looking at our atomic weights, we know that hydrogen has an atomic weight of 1.01 atomic mass units, meaning that 1 mole of hydrogen atoms will weigh 1.01 grams. In other words, 1.01 grams of hydrogen has 6.022 times 10 to the power 23 particles in it. Furthermore, oxygen has a relative atomic weight of 16.00 atomic mass units, meaning 1 mole of oxygen atoms will weigh 16.00 grams, and so on. Just a little point to notice here. Hydrogen and oxygen typically exist as diatomic molecules, which is just a molecule made of 2 atoms of the same element. So if we were asked to find the molar masses of hydrogen or oxygen gas, we'd need to multiply these values by 2. So to tell the mass of 1 mole of an atom, which is called the molar mass, it's literally as easy as reading the atomic weight of the corresponding atom off the periodic table and writing this in terms of grams. Able to use this same idea when talking about molecules, as these are just combinations of atoms. For example, one molecule of water is made up of 2 hydrogens and 1 oxygen, meaning its molecular weight is equal to 2 times the atomic weight of hydrogen plus the atomic weight of oxygen, which equals 18.02. That means that 1 mole of water molecules will weigh 18.02 grams. Okay, I think it's important here to clear up a little bit of terminology that can be a bit confusing. The difference between molecular weight and molar mass. Molecular weight is simply the combined atomic masses of all the atoms in a molecule, written as a number. This is obviously going to be a tiny mass, and so it's in atomic mass units. But the key thing is that the molecular weight is equal to the mass in grams of a mole of that molecule. So to convert this into a molar mass, MR, which is the mass of 1 mole of a particular molecule, we simply write in the units grams per mole after. It's really that simple. Using our molar mass will become really useful in our mass to mole calculations.
How to calculate molar mass in 3 easy steps. First off, there are many other names for molar mass. They all tell us the mass of 1 mole of a given compound. The key is to find the atomic mass for elements, and that's right below the element symbols. Think of atomic mass as molar mass for an element. Let's find the molar mass for carbon monoxide. So we go to the periodic table, we find carbon, and we find oxygen, and we see the atomic mass there right below the element symbol. To find the molar mass, we add those 2 numbers together, and we add the units, gram per mole, and we're done. We've found the molar mass. You may have noticed that in the previous example, I rounded to 2 decimal places. Make sure you know what your teacher requires. Let's do an example, H2O. You can think of H2O as being made up of 2 hydrogen atoms and 1 oxygen atom. So we can go to the periodic table, find the atomic mass for hydrogen, and then for oxygen, and then we'll add the 2 hydrogens plus 1 oxygen to find the molar mass for H2O. But there's a quicker and easier way to do this. We can write the atomic mass for hydrogen and multiply that by 2, and then add the atomic mass for oxygen. And that'll give us the molar mass for H2O. Let's try another, NH3. So first, we look up the atomic masses on the periodic table. We have 14.01 for nitrogen and 1.01 for hydrogen. And then we're going to multiply that hydrogen by 3 because there's a subscript of 3 after the H. Once we do that, we add everything up and we have the molar mass for NH3. Pause and try these on your own. So check your work and make sure you included the units grams per mole. Just to mess with you, I included parentheses in the third one. So how do we deal with this when we have parentheses? We'll use the same process as we've been using. So first, I'll write down the atomic mass for each of the elements. And then I'll put the parentheses around the elements just like they show up in the formula. And because I have this 2 right here, I'm going to multiply everything by 2. Once I do that, I then have 40.08 plus 17.01 times 2, and then I'll just add these 2 numbers together to get the molar mass for calcium hydroxide, CaOH2. So pause and give these 2 a try. So check your work. If you're having problems, in the description there are links to full videos for each one of these compounds. There's one more type of molar mass we need to learn to calculate, and that's for what's called a hydrate. This is copper 2 sulfate pentahydrate. Penta means 5, and the little dot means those 5 water molecules are around the copper. To calculate the molar mass, we'll first find the molar mass of the copper sulfate, and then we'll find the mass of the water. Once we have those, we'll add the copper sulfate to 5 times the mass of the water molecule. That's because we have 5 water molecules. We add this all together, and that's the molar mass for copper 2 sulfate pentahydrate. Pause and try this one. So check your work if you had.
Hey guys, hope you're well. So this lesson is all going to be about this formula over here. So the N stands for mole. Now you see there's a small m and there's a capital M. Don't confuse those, okay? So the small m is the mass, or let's say the given mass, okay? This will all make sense when we do some examples. That's the given mass. And then the capital M is called molar mass. Okay, and what that is it's the mass on the periodic table, and it's measured in grams per mole. So you write it like that. Okay, this will all make sense as we do some examples. So what I want us to do now is answer the following question. So this question says, how many moles are there in 88 grams of CO2? Okay, now by the way, this given mass is also measured in grams. So what we can do is we use this formula over here. Okay, so we say N equals to M over capital M. Now look how easy this is. They gave us 88 grams. So that is the small m. The small m is the given mass. And so you're going to say 88 over. Now, to calculate this part over here, this is the mass on the periodic table. So if you look at CO2, well, what we can see is that is going to be one carbon atom. Okay, so it's one carbon atom plus, and then there's two oxygens over here. So two oxygens, okay? And so that would be one carbon atom, which has a mass of 12, and then two oxygens now oxygen has a mass of 16. So if you work this out correctly, you should get 44. And then remember that the units of capital M would be grams per mole. So you're going to say grams per mole. And so you're going to go put that number down here at the bottom. And then if you had to calculate this, you're going to end up with 2 mole. So here's another example, and then as we go along in this lesson, I'm going to give you more questions like this, but then I'm also going to start changing the questions up where you're going to have to start using this formula in different ways. So it says, how many moles are there in 54 grams of H2O? Okay, so we're going to say N equals to M over capital M. Now remember that the small m is the given mass. The big M is the molar mass, which is from the periodic table. And then N is the mole. So we're going to say N is equal to, now the given mass is 54. That's what they gave us, 54. Now the molar mass, you have to go get that on the periodic table. So this is H2O. So that means the molar mass of H2O would be, there's two hydrogens. There's two hydrogens. And there is one oxygen. And so the mass of that would be 2 multiplied by 1 plus 1 multiplied by oxygen, which is 16. And if you had to work that out, you would get 18. And then the units is grams per mole. So I need to say 18 grams per mole. So I put an 18 over there. And if you had to go work this out, you'd end up with 3 mole. Here's another one. So how many moles are there in 49 grams of H2SO4? Okay, so we know that to calculate moles, you're going to say N equals to M over capital M. Now remember, small m is the given mass, which must always be measured in grams. And then the capital M is the molar mass, which is the mass that you get on the periodic table. And then N is the mole. Okay, so the given mass is 49. Now, H2SO4. So what that is to work out the molar mass of H2SO4, well, there is 2 hydrogens. So 2 hydrogens. There is 1 sulfur atom. Okay, so let's just write that a bit better. 1 sulfur atom and 4 oxygen atoms. 4 oxygens. And so to work out the mass, that would be 2 times 1, because each hydrogen has a mass of 1. 1 multiplied by sulfur's mass, which is 32. And then 4 oxygens. Each oxygen has a mass of 16. And if you had to go calculate that, you end up with 98. Now the units of that is grams per mole. So you could put 98 over there, and if you had to go calculate that, you're going to get 0.5 mole. Now, in the next questions, I'm going to show you, the next question coming up after this one, how to change this formula and use it in different ways. Okay, so let's do that. So what we can do is we can make a triangle. So you know the triangles that I've showed you in previous chapters, like maybe in electricity, we've got these triangles where we've got a V, I, R, or maybe you've seen other ones like W, V, and Q, or maybe you've seen Q, I, and T, for example. Now, when we have triangles like that, it makes it easier to work with them, okay, and to do different things. So here you see this one's at the top. So the one that's at the top is always the top part of the triangle, okay? And then the other two you could just put at the bottom. So the N you could put there, and then the capital M you could put there. So now you could make a whole bunch of different formulas. Let's say you're trying to get this one by itself. Well, we know that if that one's at the top, then the other two at the bottom are next to each other, so you would multiply them like that, okay? Or maybe you want to get this one by itself. Or that one you wouldn't really need to get, because that one's the one that's on the periodic table, okay? But let's just say maybe they gave you a weird question where... Oh no, I don't think they'll do that, so don't worry about that one. And then obviously to work out this one over here, oh no, let me actually go back to this one. They could sometimes do something weird where they give you like a made-up molecule that is not on the periodic table. And then they ask you to calculate this part. Well, to do that, you'll just say, this is at the top and this is at the bottom. So that's at the top, that's at the bottom. And then lastly, if we need to calculate this one, well, we know how to do that one already because this M is at the top, and then the big M is at the bottom, and then you just get back to this formula over here. Okay, so you need to know how to use all three of these. And so for the remainder of this lesson, I'm going to give you some questions that's going to help you practice the different types. So here's our next question. So it says, determine the mass in 3 moles of CO2. Okay, so we know that we've got these formulas, okay? Now, we know that N stands for mole. The small m stands for mass, or given mass, if they give you a mass, and then capital M is the molar mass. Now remember that the molar mass is the one that is on the periodic table. So they want us to calculate the mass, not the molar mass. That just means the normal mass, so that's this one, okay? So we need to get a formula with this one, and so that's over here. And so we could say that that mass is equal to the number of moles multiplied by the molar mass. So that's going to be equal to 3, because they said there's 3 moles multiplied. Now, the molar mass is from the periodic table. So to calculate the molar mass of CO2, well, there is going to be one carbon atom, and then there's going to be 2 oxygen atoms. So the mass would be 1 times 12 plus 2 times the mass of oxygen, which is 16, and that's going to give you 44 grams per mole. So you can put 44 over here, and if you had to go work that out, you would end up with 132 grams. Oh, just like that. Yeah, you're just going to say 132 grams. You're not going to say grams per mole. The only time you say grams per mole is when you're working out the capital M, which we've just done here on the periodic table. So for this one, you just say grams. Okay, let's do some more examples. This one says, determine the mass of 9 mole of NaOH. So if we have our triangle over here, then if they want us to calculate mass, well, that's this one over here. So that's going to be N multiplied by capital M. Okay, so we're going to use that formula. And so the number of moles is 9. And then you need to get the mass on the periodic table. So whoopsie, why am I writing so weird? NaOH. Well, that's going to be 1 Na atom. You can see 1 Na plus 1 oxygen plus 1 hydrogen plus 1 hydrogen. And so that's going to be the mass of Na, 23, the mass of oxygen, 16, and the mass of hydrogen is 1. So that's going to be 40 grams per mole. And so we could say 9 times 40, and that's going to be 360 grams. Here's our last question. So it says, how many moles are there in 50 grams of CaCO3? Okay, so if we have that triangle, then they want the number of moles now. So they want this. So number of moles is equal to whatever's at the top divided by the capital M, which is molar mass. So they remember that N is mole, M is the given mass, and here they've given it to us, and then capital M is the molar mass, which is on the periodic table. So we're going to say N equals to M over capital M, and so the mass is going to be 50. Now, to go work out the molar mass of calcium carbonate, or CaCO3, then that's going to be 1 calcium atom, 1 calcium, plus 1 carbon, plus 3 oxygens. Okay, and so that's going to be 1 calcium, which is 40 grams per mole, plus 1 carbon, which is 12, plus 3 oxygens. Now each oxygen is 16. So if you had to go calculate this, you get 100 grams per mole. So that's going to be over 100. And so if you had to go work this out, you're going to end up with 0.5 mole.